Hi there and welcome back to the channel. Throughout this series of videos, you will be introduced to topics in optimal control and estimation in a way that you can draw almost complete idea about optimal control and optimal observers. Most of the introduced materials during this journey is borrowed from the book, Applied Optimal Control Optimization, Estimation, and Control, which written by Arthur Bryson. Let me first introduce the parameter optimization definition when constraints are not active. Any parameterized optimal-based problem involves computing the values of m parameters, u1 through um. These parameters optimizes a performance index which is function of these parameters as shown by the function L capital. L is a scalar function. Let us combine all of these parameters in one vector u. Keep in mind that these parameters are sometimes called decision variables or vectors. Then we can write the performance index as L of u. In order to find the necessary condition for a minimum, let us assume that L of u has first and second partial derivatives everywhere in the decision space. Necessary conditions for minimum are: the first partial derivative is delta L over delta u. Equalizing this derivative to 0 is the first condition for optimality, as we can see later. The second partial derivative is as shown. This derivative is an m by m matrix. Each element is derived by the given formula. This matrix shows the nature of the optimum point, as will be seen in the upcoming slides. Thus, the necessary conditions for a minimum are: the first derivative is equal to 0, from which a set of points could be computed. At these points, the index function L of u is minimum if the second derivative of the function at these points is positive semi-definite, i.e., the function has eigenvalues that are 0 or positive. The first equation here gives a point in the decision space called the stationary point or points. A stationary point of a function is a point where the derivative of the function is equal to 0. These points are called stationary because at them, the function is neither increasing nor decreasing. Now, as we have formulated the conditions for a minimum point, let us extend them a little bit for defining a local minimum. Sufficient conditions for a local minimum are: equalizing the first derivative to 0. Remember, this gives stationary points. And at the stationary point, the index function L of u has a positive definite second-order derivative, i.e., the all eigenvalues are positive. Before jumping to examples, let us go through two important points. The first point happens when we have both first and second partial derivatives are 0. The second derivatives to be 0 means that either the determinist of the matrix is 0 or one or more of the matrix eigenvalues are 0. When this occurs, the corresponding stationary point is known as a singular point. A singular point of a function is a point where the function has a nasty behavior, such as a cusp or a point of self-intersection. The last point happens when the index function is a linear combination of the parameters. Here, the second partial derivative of the index performance is 0 everywhere in the decision space. So, in general, a minimum does not exist. For this situation, we may require more information to define the stationary points as minimum points. Let us now apply what we have learned so far on some examples. The following examples are two dimensions, meaning that there are only two parameters or two variables. Remember that the concepts introduced throughout these examples are extendable for problems with m variables. Let us having an index of performance with two parameters u1 and u2. The first form of the index is as shown. This index can be reformulated as vector and matrix form as. The formed matrix is known as the Hessian matrix, which is a square matrix of the second-order partial derivatives of a scalar-valued function. This is a special case for quadratic functions. Now, as this matrix has two positive eigenvalues, then the stationary point is a local minimum. In fact, as we have a quadratic index performance, this local minimum is a global minimum. Why don't you go ahead and drive the first and second derivatives and check the optimality of the stationary point? You first need to find the stationary points from the first derivative. Then, you need to perform the second derivative and find the definite of the matrix. In the second example, the index of performance is given as, and by examining the eigenvalues of the matrix, we can say we have a saddle point. Saddle points of a multivariable function are those points in its domain where the tangent is parallel to the horizontal axis, but this point tends to be neither a local maximum nor a local minimum. Lastly, we have a performance index as shown. After writing it in the vector and matrix format, we can examine the Hessian matrix eigenvalues. As the matrix has a zero eigenvalue, then we have a singular point. In the next video I am going to introduce the same problem but with equal constraints and determine the necessary conditions for stationary points. Thanks for watching and please do not forget to like the video. See you soon, hopefully.